This is the first part, and I'm going to make a series of videos. So here, the first one, developing a microprocessor. Examine a simple architecture based on the MIPS processor in order to acquire an understanding of how RISC microprocessors are built. Okay, MIPS, microprocessors without interlocked pipeline stages. Where pipeline stages is a further enhancement which can increase performance significantly. We'll not be exploring this aspect of the design, only the architecture. Assume each instruction executed in a single clock cycle. Use both the rising and falling edges to trigger the circuits. RISC and CISC. MIPS is a RISC reduced instruction set computer. CPU, which means it may take several instructions to perform a C-code operation in a comparison to a CISC, complex instruction set computer. Your home x86 PC understands CISC instructions, but it is internally a RISC processor so that it can operate faster. 68HC11 is also a CISC CPU. The instructions are CISC and the hardware runs it directly. CISC designs can become very large, complex, so we shall discuss those later once we have a general idea of how a CPU works. Design the simulation tool. Logism evolution custom version based on the original Logism tool no longer developed. Digital circuit simulator allows for circuit hierarchy, and free software tool requires Java runs on all platforms. Secondary file required for PLA component. Serve often use versioning to avoid potential corruption. Restart tool every so often. Okay. What do we need? Need an idea of the types of instruction needed in a CPU to perform the necessary step found in modern programming languages. Mostly all programming languages are the same. Many have different syntax and available functions, but their base language utilizes the same structures. Very high level languages have constructs which can be built based on these structures. Basic instruction. The pseudocode illustrates almost all the operations a CPU need to perform. Avoid subroutines. Read or write variables from the other variables and constants. Compare variables with other variables or constant numbers. Program control conditional and non-conditional. Basic math and logic functions. And here we have a pseudocode coding. Okay, let's look at that. Storage variables. Need a place to store working information variables. Register can store information, fast speed, but large in size, which limits how many we can use. Larger circuit is equal to slower circuit. Store variables in memory. RAM. RAM is less expensive than registers, smaller but slower. Can only access one word at a time. Fair compromise, as a CPU can only execute one instruction at a time. Storage variables. Use register for computations, limited number. Load register from RAM. Process data could be many steps. Store results back to RAM. Refer to registers with R in front of R0 for the registers 0. R1 for the register 1, etc. Always referring to constant of the register during read or write. Registers are managed by the register file component array of registers. And that's it for this video. I'm going to go ahead and continue this one on my next videos. I hope you guys find this video helpful. Thanks for watching. Don't forget to subscribe my channel. See you guys on